Welcome friends to another session on mathematical modeling. Let us discuss the mathematical modeling in population dynamics and also some compartment models. Effects of immigration and emigration on population size. If there is immigration into the population from outside at a rate proportional to the population size, the effect is equivalent to increasing the birth rate. Similarly, if there is immigration from the population at a rate proportional to the population size, the effect is the same as that of increase in the death rate. If, however, immigration and emigration take place at constant rate I and E respectively, then dx by dt is equal to bx plus I minus E, which is equal to Ax plus k. Integrating this equation, we get x of t plus k by a is equal to x of 0 plus k by a into e raised to a t. The model also applies to growth of populations of bacteria and microorganisms, to the increase of volume of timber in forest, to the growth of malignant cells, etc. In the case of forest, planting of new plants will correspond to immigration and cutting of trees will correspond to emigration. Next, compartment models. In the last sections, we got mathematical models in terms of ordinary differential equations of the first order, in all of which variables were separable. In the present section, we get models in terms of linear differential equations of first order. We also use here the principle of continuity, that is, that the gain in amount of substance in a medium in any time is equal to the excess of amount that has entered the medium in the time over the amount that has left the medium in this time. A simple compartment model. Let a vessel contain a volume V of a solution with concentration C of t of a substance at a time t. See the figure. Let a solution with constant concentration C in an overhead tank enter the vessel at a constant rate R, and after mixing thoroughly with the solution in the vessel, let the mixture with concentration C t leave the vessel at the same rate R, so that the volume of the solution in the vessel remains V. Using the principle of continuity, we get V into C of t plus delta t minus C of t is equal to R into C into delta t minus R C of t delta t plus 0 delta t, giving V into dC by dt plus R into C is equal to R into capital C. Integrating C of t is equal to C of 0 into exponent minus R by V t plus C into 1 minus exponent minus R by V t, and as t tends to infinity, C of t tends to capital C, so that ultimately the vessel has the same concentration as the overhead tank. Since C of t is equal to C minus 0 into exponential minus R by V t, if C greater than C naught, the concentration in the vessel increases to C. On the other hand, if C is less than C naught, the concentration in the vessel decreases to C. See the figure. If the rate R dash at which the solution leaves the vessel is less than capital R, the equations of continuity give d by dt of V naught plus R minus R dash into t all into C of t, which is equal to R C minus R dash into C t, where V is the initial volume of the solution in the vessel. This is also a linear differential equation of the first order. Diffusion of glucose or a medicine in the bloodstream. Let the volume of the blood in the human body be capital V, and let the initial concentration of glucose in the bloodstream be C of 0. Let glucose be introduced in the blood stream at a constant rate I. Glucose is also removed from the bloodstream due to the psychological needs of the human body at a rate proportional to C of t. So, that the continuity principle gives V into dC by dt is equal to I minus k into C, which is similar to third equation. Now, let a dose D of a medicine be given to a patient at a regular intervals of duration capital T each. The medicine also disappears from the system at a rate proportional to C of t. The concentration of the medicine in the bloodstream, then the differential equation given by the continuity principle is V into dC by dt is equal to minus k into C. Integrating this equation, we get C of t is equal to d into exponential minus k by v into t, where 0 less than or equal to t less than capital T. At a time capital T, the residue of the first dose is d into exponential minus k by v into t, and now another dose capital D is given. So, that we get C of t is equal to d into exponential minus k by v into t plus d all into exponential minus k by v into t minus t, which is equal to d into exponential minus k by v into t plus d into exponential minus k by v t minus t, that is t is less than or equal to t less than 2t. The first term gives the residual of the first dose and the second term gives the second dose. Proceeding in the same way, we get after n doses have been given, C of t is equal to d into exponential minus k by v into t plus d into exponential minus k by v into t minus capital T plus d into exponential minus k by v into t minus 2t plus etcetera plus d into exponential minus k by v whole into t minus n minus I into t. That is same as d into exponential minus k by v into t into 1 plus exponential k by v into t plus exponential 2k by v into t plus etcetera plus exponential n minus 1 into k by v t, which is same as d into exponential minus k by v into t whole into exponential n k by v into t minus 1 divided by exponential k by v into t minus 1 for n minus 1 capital T less than small t less than n into capital T. That is C into n t minus 0 is equal to d into 1 minus exponential minus k by v into n t divided by exponential k into t by v minus 1. That is C into n t plus 0 is equal to d into exponential k t by v minus exponential minus k by v into n t whole divided by exponential k into t by v minus 1. Thus, the concentration never exceeds d by 1 minus exponential minus k by v into t. The graph of CT is shown in the figure. Thus, in each interval concentration decreases. In any interval, the concentration is maximum at the beginning of this interval and thus maximum concentration at the beginning of the interval goes on increasing G as the number of intervals increases, but the maximum value is always below d by 1 minus e raised to minus k t by v. The minimum value in an interval occurs at the end of each interval. This also increases, but it lies below d by exponential of k into t by v minus 1. The concentration curve is piecewise continuous and has point of discontinuity at t, 2t, 3t, etc. By injecting glucose or penicillin in a blood and fitting curve to the data, we can estimate the value of k and v. In particular, This gives a method for finding the volume of blood in the human body. Next, we will discuss mathematical modeling in dynamics through ordinary differential equations of first order. Let a particle travel a distance x in time t in a straight line, then its velocity v is given by dx by dt and its acceleration is given by dv by dt, which is same as dv by dx into dx by dt, which is equal to v into dv by dx is equal to d square x by dt square. Simple harmonic motion. Here a particle moves in a straight line in such a manner that its acceleration is always proportional to its distance from the origin and is always directed towards the origin. So, that v into dv by dx is equal to minus mu into x. Integrating, v square is equal to mu into a square minus x square, where the particle is initially at rest at x equal to a. Equation 16 gives dx by dt is equal to root mu into root of a square minus x square. We take the negative sign since velocity increases as x decreases. See the figure. Integrating again and using the condition that at t is equal to 0, x equal to a, we get x of t is equal to a into cos root mu of t. So, that v of t is equal to minus a into root mu into sin into root mu t. Thus, in simple harmonic motion, both displacement and velocity are periodic function with period 2 pi by root mu. The particle starts from A with 0 velocity and moves towards 0 with increasing velocity and reaches 0 at time 2 pi by root mu with velocity root mu into a. It continues to move in the same direction, but now with decreasing velocity till it reaches a dash, where 0 a dash is equal to a, where its velocity is again 0. It then begins moving towards 0 with increasing velocity and reaches 0 with velocity root mu into a, and again comes to rest at a after a total time period 2 pi by root mu. The periodic motion then repeats itself. As one example of simple harmonic motion, consider a particle of mass m attached to one end of a perfectly elastic string, the other end of which is attached to a fixed point 0. See the figure. The particle moves under gravity in vacuum. Let I naught be the natural length of the string and let A be its extension when the particle is in equilibrium, so that by Hooke's law mg is equal to T naught, which is equal to lambda into A by I naught, where lambda is the coefficient of elasticity. Now, let the string be further stretched a distance c and then the mass be left free. The equation of motion, which states that mass into acceleration in any direction is equal to force on the particle in that direction, which gives m into v into dv by dx is equal to m into g minus t, which is equal to mg minus lambda into a plus x by I naught, which is equal to minus lambda x by I naught, or v into dv by dx is equal to lambda x by m into I naught, which is same as minus g into x by a, which gives a simple harmonic motion with time period mg is equal to T naught, which is same as 2 pi into root of a by g. Next, we will discuss mathematical modeling of geometrical problems through ordinary differential equations of first order. Simple geometrical problems. Many geometrical entities can be expressed in terms of derivatives, and as such relations between these entities can give rise to differential equations whose solution will give us a family of curves for which the given relation between geometrical entities is satisfied. As an example, let us find curves for which tangent at a point is always perpendicular to the line joining the point to the origin. The slope of the tangent is dy by dx, and the slope of line joining the point ordered pair xy to the origin is y by x. And since these lines are given to be orthogonal, dy by dx is equal to minus x by y. Integrating, we get x square plus y square is equal to a square, which represent a family of concentric circle. Next, let us find curves for which of the normal on the x axis is of constant length. This condition gives y into dy by dx is equal to k. Integrating, we get y square is equal to 2 into k into x plus a, which represents a family of parabolas all with the same axis and same length of latus rectum. Now, let us find curves for which tangent makes a constant angle with the radius vector. Here, it is convenient to use polar coordinates, and the conditions of the problem gives r into d theta by dr, which is equal to minus tan alpha. Integrating, we get r is equal to a into e raised to theta cot alpha, which represents a family of equiangular spirals. Orthogonal trajectories. Let f of x y a is equal to 0 represent a family or curves, one curve for each value of the parameter a. Differentiating, we get dou f by dou x plus dou f by dou y into dy by dx is equal to 0. Eliminating a between equation 29 and 31, we get a differential equation of the first order phi of x y comma dy by dx is equal to 0, of which equation 29 is the general solution. Now, we want a family of curves cutting every member of equation 29 at right angle at all points of intersection. At a point of intersection of the two curves x comma y are the same, but the slope of the second curve is negative reciprocal of the slope of the first curve. As such, differential equation of the family of orthogonal trajectory is phi of x comma y minus 1 by dy by dx is equal to 0. Integrating equation 33, we get g of x y b is equal to 0, which give the orthogonal trajectories of the family equation 29. Let the original family be y is equal to mx. When m is a parameter, then dy by dx equal to m, and eliminating m, we get the differential equation of this concurrent family of straight lines as y by x is equal to dy by dx. To get the orthogonal trajectories, we replace dy by dx by minus 1 by dy by dx to get y by x is equal to minus 1 by dy by dx. Integrating this equation, we get x square plus y square is equal to a square, which gives the orthogonal trajectories as concentric circles. See the figure. Now, let us find the orthogonal trajectories of the family of confocal conics given by x square by a square plus lambda plus y square by b square plus lambda is equal to 1, where lambda is a parameter. Differentiating, we get x square by a square plus lambda plus y square by b square plus lambda into dy by dx equal to 0. Eliminating lambda between equation 37 and 38, we get xp minus y into x plus py, which is equal to p into a square minus b square, where p is equal to dy by dx. To get the orthogonal trajectories, we replace p by minus 1 by p to get minus x by p minus y into x minus y by p, which is equal to minus 1 by p into a square minus b square, or x p minus y into x plus py, which is equal to p into a square minus b square. However, equation 39 and 40 are identical. As such, the family of confocal conics is self-orthogonal. That is, for every conic of the family, there is another with the same foci which cuts it at right angles. One family consisting of confocal ellipses and other consisting of confocal hyperbolas with the same foci. See the figure. Now, we discuss in polar coordinates after getting the differential equation of the family of curves. We have to replace r into d theta by dr by 1 by r into d theta by dr and then integrate the resulting differential equation. Then, if the original family is r is equal to 2a into cos theta with a greater than 0 as a parameter, its differential equation is obtained by eliminating a between equation 41 and dr by d theta is equal to minus 2 into a sin theta. To get r into d theta by dr is equal to minus cot theta. Replacing r into d theta by dr by minus r into d theta dr inverse, we get r into d theta by dr is equal to tan theta. Integrating, we get r is equal to 2 into b sin theta. The orthogonal trajectories are shown in the figure. The circles of both families pass through the origin, but while the center of one family lies on x axis, the centers of the orthogonal family lies on y axis. Prey-predator models. Let x of t, y of t be populations of the prey and predator species at time t. We assume that if there are no predators, the prey species will grow at a rate proportional to the population of the prey species, and if there are no prey, the predator species will decline at a rate proportional to the population of the predator species. The presence of both predators and prey is beneficial to growth of predator species and is harmful to growth of prey species. More specifically, the predator species increases and the prey species decreases at rates proportional to the product of the two populations. These assumptions give the system of non-linear first ordered ordinary differential equations. Dx by dt is equal to a into x minus bxy, which is equal to x into a minus by, where a comma b greater than 0, and dy by dt is equal to minus py plus qxy, which is equal to minus y into p minus qx, where p comma q greater than 0. Now, dx by dt and dy by dt both vanish if x equal to xc, which is equal to p by q, y equal to ye, which is equal to a by b. This comes under nonlinear models. We will discuss it in details later. Let us summarize what we have discussed in this session. In this session, we discussed about effects of immigration and emigration on population size. Moreover, we explained mathematical modeling in dynamics through ordinary differential equations of first order. We also concentrated on mathematical modeling of geometrical problems through ordinary differential equations of first order. there are few assignments for you to work out. First one, in Gulliver's Travels, the Lilliputians decided to feed Gulliver 1728 times as much as food as Lilliputian ate. They reasoned that since Gulliver was 12 times their height, his volume was 123 is equal to 1728 times the volume of Lilliputian, and so he required 1728 times the amount of food of one of them ate. Why was their reasoning wrong? What is the correct answer? Second question, two college administrators are trying to decide on admissions policy so as to obtain the best possible students for their college. They each have different ideas on how important various traits are in a good student. Can you suggest a theoretical plan for helping them? A practical one. What if 3 administrators are involved? Note, the time and money required for extensive testing are not available. Only the administrators and their opinions are available. Third question, in industrial chemical process, yield is frequently highly depend on temperature and pressure, but these are limited in range by technological and economic considerations. The amount of impurities also depends on temperature and pressure. Describe a graphical approach for obtaining maximum yield when one impurity cannot exceed a certain value. Fourth one, what do you mean by compartment models? Fifth one, find a family of curve. For each curve, the length of the tangent intercepted between the axes is of constant length. Draw the curves. For further reading, you can refer following books. First one, An Introduction to Mathematical Modeling by Edward A. Benter, Wiley-Interscience publication 1978. Second, Concept of Mathematical Modeling, Walter J. Mayer, Dover publication 1984. Third, Mathematical Modeling, Classroom Notes in Applied Mathematics, edited by Murray S. Clamkin, Swayam publication 1995. Fourth one, Differential Equation Models, Volume 1, edited by Martin Braun, C. S. Coleman, D. A. Drew. And the last one, A Concrete Approach to Mathematical Modeling by Mike Masterton Gibbons, Wiley-Interscience publication 1995. Thank you everybody. Hope you have followed these sessions. Let us meet in another session with another topic. Till then, bye.